Thank you very much for the invitation, and it's really my honor to share some of my work and my research with you all through this webinar. So I guess I'll get started into it. I'll be talking today about enabling ubiquitous solar photovoltaic power through power electronics design and also through a little bit of control. So thank you again for having me, and I'll get started. All right, we already read my background, but just to give you a visual of the different places I've been. I'm originally from the US, so I did my undergrad and graduate studies there. Then I went to Korea to live for about 4 years and start my career as a professor. And now I'm in Taiwan and working here as a professor. I also did a little bit of work in industry, but mostly I've done research as a professor as part of my career. So if you ever get the chance to visit Taipei or Taiwan, we have a beautiful campus here. Taiwan's a really small country right there in the map. And when the pandemic is over, I hope you will all get a chance to visit. It's lovely, but not in summer. Come in a non-summer time. It's very hot. So jumping into the topic. So I work on solar photovoltaics. I've been interested in solar for a long time. And of course, we have our traditional PV panels that you may think of when you think of solar photovoltaic, solar PV. But I like to think about where else we can use power. So when I go out in the morning, I look at the sun, and it's not always a lot of sun, but there's always some sunshine or some direct light. And I think about how we can utilize this power for everything, not just for our traditional energy that's hitting maybe a panel on a roof or in a field, but other things as well. So in the modern day, and actually this is our modern reality of right now, so even in the time of the pandemic, we are looking at how to transform energy. And mostly we're doing this because we need cleaner forms of electricity, especially as climate change is becoming more and more affecting all of the countries around the world. So my research question is, how can we enable solar in more applications? So we have some buildings, but building integrated photovoltaics is another area of research. How can we get photovoltaics involved in larger buildings, not just ones that are out in large fields, but in cities? Could we use photovoltaic solar for vehicles? Maybe not to power them completely, but to add a little bit extra power to them so they can go a little bit longer and actually reduce the battery stress on the battery. So could we use it for vehicles? Could we use it in things that people wear on their person? So hats, phones, watches, bags, things like that. So my curiosity is to, how do we use photovoltaics here? And as someone who's very interested in solar, I said, well, I'm going to use what we have, what tools are there right now, and I'm going to try to do everything I can to power all of everything from solar. So the thing I started with is, maybe you've seen something like this. It's usually for outdoor use, like a panel that can fold in half, and you can plug it in. It has a little USB adapter here, and you can see when it's rated for 6 watts, so you should be able to get 6 watts of it when it's in the sun. But I put it out near my office, and I put it where I could get it to stand up in the sun. And you'll see here, just a little bit of this corner is shaded. And of the rated power, I was able to get 3.5 watts. So that's about 58%, which is not bad, but it definitely wasn't the high power I wanted. So even with this little bit of shading here, we didn't quite get the full amount of power. So I said, well, what about when it's half shaded? Because this condition may come up a lot. So what happens if we get half of this thing shaded? We would like to still get 50% because we're still getting 50% of the solar power. But we see that when we have it half shaded like this, we only get 0.3 watts out, and that's about 5%. That is just enough to charge most batteries, but not, or for example, for a phone, but not very quickly. And some applications won't even charge at this level of power. So clearly the solutions that are at least commercially available for mobile, or movable, portable solar power are not very good. And I wanted to understand this problem. And so this is what we're going to try to address through the talk today. So I'll be coming back to this in a little bit, but first I wanted to cover a little bit more about solar photovoltaic basics, because most people don't know all of the basics around it. So I'll cover the basics, then I'll talk about some emerging PV applications. So what kind of applications are we talking about with these kind of solar applications? And then we'll talk about some of the converter architecture approaches in using power electronics converters. Some of the data that we've looked at for wearables specifically, that's the area that we're looking at more closely for our research. And then also a maximum power point tracking algorithm that we've been looking at for these types of applications. So I'm going to start with the solar photovoltaic basics. So just to give a really broad background, photovoltaic materials are taking sunlight and they're turning them into electricity, DC power for us to use. The most common ones that you'll see in the large panels that may be on roofs or in fields, for example, are silicon, crystalline silicon. So you have a monocrystalline or a polycrystalline. These are made out of silicon and relatively cheap. They've been in use since the 1950s and have really matured in terms of their technology. There's also thin film technologies, which are have the potential to be actually flexible. Not all of them are designed that way. For example, these thin film, this one shown on the left here is a thin film, but this is a rigid thin film one. They tend to have advantages in manufacturing. The cost of manufacturing tends to be lower, but their efficiency is a little bit lower as well. So the next graph I'll show has some of that data. Another type, which is multi-junction. These ones are used for space and are generally not used for terrestrial applications. They can be in certain situations, but they're quite expensive. Each of these panels is going to be at least 10, maybe even 20 times, maybe even more that, more expensive than this crystalline type, or even the thin film technologies. So those are definitely satellite applications or very high price applications. There's also some emerging types. Dye sensitized cells, perovskites are really big in the solar cell development world, and some organic. They are looking for low cost solutions and then sometimes unique, like semi-transparent and flexible applications as well. So in terms of efficiency, this is kind of a busy graph, but if you're ever curious about where the efficiency for each type of solar cell is, this is a resource from NREL. I recommend going to their website to find this. They'll update it I think every quarter about, or at least every year. And you can look at the different types of materials and find the efficiency for that. So the ones that we use, for example, the silicon crystalline is the blue one. You kind of follow, you can see that it isn't really going up much. It's kind of matured, it's kind of leveled off. So those efficiencies are the best ones around 27, 26% efficiency, but a lot of the commercial ones are still around the 21, 22, or 23 efficiency here. And the big innovations recently are in the emerging types coming up here, but notice they're also a little bit lower efficiency. So whenever you're choosing the type of solar cell for the application, you have to think about form factor. Do you need a rigid cell? Does it need to be behind glass? Does it need to take a lot of temperature? Does it need to be flexible? What's the cost point? Things like that. So those are resources. You can look up more information on that if you're curious about the cells. And just from the electrical standpoint, how do they work? I'm just doing the really basic part. What we do is we take the two different materials. One is p-doped and one is n-doped. This is also the same as a diode, actually. So a photovoltaic cell is actually just a very large and short, fat diode. So this depletion region, or sorry, space charge region here is where the electric field is generated when you put two of the materials together. And if a photon comes in this region and excites an electron out of the valence band into the conduction band, you'll have a positively charged hole and a negatively charged electron. If those are in electric field, they're going to go in opposite directions, and that creates your current. So you want to have a very large region here, space charge region. So if the solar cell is essentially extending that vertically and making this large region very large, and then when the light hits it, it's going to create current from that. So when we look at those characteristics, so for people doing power electronics, we want to understand generally how they work, and we want to model them as a circuit, because we want to understand how that circuit is going to interact with the power electronic circuit that attaches to that. So we would have our p-n junction here. And so here, before the picture was long and we put it on its side, and now you can see it's a long extended one. And the light comes in on one side and it's going to create the whole pair there, and then we can get our voltage out of here. So like I said, that's a p-n junction. So actually, if we're trying to model this electrically, we would say that we can model it as a diode. It has a nonlinear equation, but it's a well-known equation, so you can model it as a diode. And we have some other characteristics here as well. Those are sometimes modeled, but they don't have to be. I won't go into the details here. If you're really curious about this, I do have more work on modeling of PVs, but the important components are the diode, which is the property of the p-n junction, and the current here. This is the photocurrent. So this is the electricity, the electrons, currents, that is generated from the photons coming into the p-n junction and creating the current from that. So the more light that you come in, the higher the intensity of light hitting the panel, the more current, this photocurrent, that you will generate. So if we want to model that from just a basic model of that in electrical components, we use just these two components. And this is from a different source, which is a really great source on modeling. So you want to just model these two different things. And just to conceptualize what this is, if we break down each of these components, this is a photocurrent, so a current source that's going to be the level of the photocurrent. And so that's just a constant current here. And the diode is going to have this exponential curvature, which is shown here. And when we do KCL, Kirchhoff's current law, right, we have the current coming in here, we subtract the current through this diode, and the current coming out of the whole box, the PV, will be the result of that. So if you take this current and you subtract this exponential, you'll get this type of, it's kind of like a knee. We call it, this is the knee of the curve. So it's a nonlinear curve and it is bounded. So it has one point here. I guess this is the next slide, so I'll get to that second. These are just showing the equations. I'm not going to go into those, but these are the characteristics of the photovoltaic panel. So one cell or a whole panel can be modeled in this way. And so this is a common circuit symbol for a photovoltaic, and we can get the voltage and the current characteristics from that based on this curve. So we see that there's an open circuit voltage. So if you open circuit, you don't connect anything around here, you're just going to get the highest voltage, which is going to be the open circuit voltage, which would be this value. And if we short this, we short these two together, we would get the short circuit current, and that would be the highest current that the PV can generate for the illumination that's hitting the panel. And both of those points though are actually zero power. So if we want to get the maximum power from our photovoltaic cell, there's actually one point here. I call that the maximum power point, so MPP, and that's where we want to operate in order to maximize the power out of our cell. So generally, we would want our controller, our converter, that will be connected to this PV to operate the system at that point. Another way to look at that is here's the IV curve, so the current versus the voltage characteristics, and you can see this maximum power point. That where this point actually comes from is the power versus voltage curve, which you can see on the right. And as you do the calculation for power on here, what it will do is follow this curve. And so you'll see that these maximum points at the top of the hill here is right here. And it is relatively close to the open circuit voltage and also to the open circuit or short circuit current. Okay, I will go to the next part. So the thing to remember about this for the applications I'm going to talk about is that this point, this maximum power point and the curve, they change with two major factors. One is called irradiance. This is the light intensity. It's measured in watts per meter squared. So if you have a certain area, you have a certain amount of power hitting that. On a really sunny day, you'll have more power than on a less sunny day. So 1,000 watts per meter squared is like a very, very pretty sunny day outside, direct sunlight. And so you would be able to get this type of curve, and it would have a higher short circuit current. It could produce more current. However, when the light decreases, the current here, the current characteristics are going to decrease. So if you have one cell that's getting a lot of current or a lot of sunlight, it'll look like this. If you get one that's maybe shaded or just not getting as much, is going to maybe produce a lot less. So the characteristics change with the irradiance, and the current characteristics are directly proportional. So if it's good sunnier, they're going to shift upwards, kind of like this. And then we also have to look at temperature. Temperature is inversely proportional to the open circuit voltage. And this is just based on the semiconductor properties. The same thing happens with a diode, actually. So if you have something that's very hot, it's a solar panel, maybe it's in a very hot place, it's getting a lot of sun and it's warming up, the voltage characteristics will actually go inward. I'm not sure which way my screen is coming in, but it's coming this way. I'll point with my mouse, it's better. And if it gets colder, so 25C would be the nominal conditions. If it gets very cold, say negative 25C, it's going to increase the voltage characteristics as shown here. So actually, photovoltaics produce more power in very sunny but cold conditions. So that would be actually a great place to use it, would be if it was cold and very sunny. Okay, so those are the characteristics and for the panels, the solar cells. And so they're affected by light changes and by temperature. So why is this important? When we put these cells together, if they're mismatched, then we're going to have some problems or some limitations, I'll say. So if we have two different cells, say one is either normal and one is degraded, or you could say one is unshaded and shaded, there's a bunch of different things that could happen. So they have different characteristics. So this one is underperforming and this one is meeting the expectation of the performance. So we can look at the IV curves first. We could plot those out and you can see the current here for each one. The blue one is the blue one here, and the green dashed line is the degraded one. If we connect these in series, which is what we normally do, because each cell tends to be pretty low in voltage, maybe 0.5 to 0.7 for a normal silicon crystalline. And so because it's such a low voltage, we usually put them in series, stack them up in order to get a higher voltage. So if we do that, like as shown here, and here are the power curves. So this is the power curve for the normal one and the power curve for the degraded one. If we put them in series and then measure the string current or change the string current and voltage, we will get these characteristics. So because they share the same current, they're in series, we can think of it as sweeping the current. So you increase the current and you measure the resulting voltage. And the voltages are based on, this is the previous slide, based on these curves. So as I say, 1 amp, we would see that both of these would have a relatively high voltage. But you'll notice once we hit 3 amps and higher, we're only going to see the voltage from one of those. So what that results in this curve is kind of stepping down. So for each of the panels, it kind of steps down once the current goes above the characteristics for the degraded one. And when we map this into the power, we see that we get these two kind of hills here. And the problem with this is that we're not able to optimize. One is that the total power is reduced. So if we went back here and we added up these two powers, it is not reaching the same value as this maximum power point of the whole curve, because when one is optimized, the other one is compromised actually. So this point is the maximum, near the maximum power point for the degraded one, but not for the normal one. So the moment we put these mismatched cells together, we're losing power actually. So the semiconductor, PV semiconductor industry that makes the panels goes through a lot of effort to reduce the mismatch as much as possible. So on the left, you can see somebody is sorting through tested cells. They'll test each of the cells. They're all usually from the same manufacturing line, but there's variance and tolerance. So they'll actually sort them into different piles. And then with the piles that have all the same characteristics, they'll make a panel out of that so that they can ensure that each one has the minimized mismatch from the beginning. But in use, things like dusting, so shown on the right, dusting or even water, like when people, after you clean it, sometimes there's actually residue left. That's other types of residue or soiling. There's also shading, there's self-shading. There's so many different types of things that can affect the panel. So people go through a lot of effort to get rid of this mismatch in order to maximize the power through these panels. So this is the state of traditional panels. But what I've been interested in is how do we embrace the solar cell mismatch while maximizing the output power? So if we're in a condition where we can't minimize, we can't get rid of this mismatch is going to happen, how can we still achieve maximum power with this? The large series applications, actually it's a totally different topic. I also study that, I'm not covering it here. We've looked at series differential power processing systems. So that's one way for these larger, more like the traditional ones here. I'm not going to cover that in this talk, but I also have work related to that. And there's a lot more in the field actually coming out. For this one, we are looking at generally lower power systems, not grid connected. So to do this, we need to rethink the system and the power architecture. And we need to use intelligent control at the converter level. So that's what we're going to try to implement in order to achieve, to work with the mismatch rather than just trying to get rid of it completely. Okay, so what kind of applications would we utilize this in? So some of them are a little bit further out, but some seem to be actually more around the corner than you might think. So from the panel, the flat panel, we can move to other applications. So this one actually on the right is a solar powered electric vehicle. Of course, it also plugs in. The solar panels provide auxiliary power. So as it's driving or while it's sitting outside, it can take additional power and charge up the battery. And this is actually a company, I think it's based in Denmark. Lightyear One is pretty interesting. They're almost coming out. I think they're coming out with their first real car soon. So if you're interested in that, I'm also following their work, although I don't think I can buy one in Taiwan where I live. So interesting work if you're interested. Another topic that we've looked at are drones, and this is a very early implementation that we did with the collaborator. But the idea is if you're flying outside anyway, you have drones. Usually drones are outside. They're getting natural light from that anyway. Drones actually do consume quite a bit of power, but could you use solar panels to help offset that and maybe make them go a little bit longer, or allow them to land and charge and then go on some mission multiple times? So if you wanted to do that, you would also have to consider some of the challenges. So for example, in all of these, there's curved PV panels. We may have shading, things are moving. So those are all things that are not challenges in traditional grid connected systems. The last picture I'm showing is for wearable photovoltaics. And this is a designer. I think she's based in the Netherlands, and she has more concept pieces. These are not commercially available, but ways of providing power, wearing power on you in order to either charge phones, or maybe you can charge something else, whatever types of smart sensors may be embedded into clothing in the future. So those are 3 applications, and there's actually many more. I think as we continue, more portable devices will hopefully be able to use photovoltaics as well. Okay, so just to go a little bit more on the solar car topic, I follow this just because I'm interested. In 2019, Toyota came out with a Prius that was covered in panels, that's shown here on the left. I wouldn't say the most beautiful implementation, not the most attractive, but it was a concept car to show that you could. And this one, I think on the right, the Lightyear One, is taking the next step and going pure electric with solar panels. So again, if you're interested, I recommend looking at those some more. For the solar drone one, actually, this is with my collaborator at National Ilan University, also in Taiwan. They developed with panels, solar panels on top of the drone. These are the space ones, actually, so they're very, very expensive. This is not a cheap application, but we wanted to show the concept. So these are PV panels on top of the drone, and it can fly and charge, and also if it lands and charge, it can charge us up some more. It offsets the battery a little bit, maybe about 5 to 10%, if I remember correctly. So this was just proving that the idea could be done, and we're still working on this as well. Okay, so now going to the topic of wearables, which is where I have focused more of the application. But I will say that even if wearables are not interesting to you, that the concept of just enabling power where photovoltaics are not going to get uniform lighting, that's really what we're trying to enable. So maybe it's wearables, maybe it's a different application, a curved surface of PVs, building integrated PVs. It could be many different things. So, but for now, I'm going to focus on our wearable applications. So we have people wear smartwatches, they're monitoring their health rate. There's even like a ring now that's a wearable. So there's different types of wearable activity monitors that are quite popular. There's new technologies about people wearing 3D motion trackers for various applications. And you could even have wearable gesture sensor. So a lot of different technologies that are relating to wearables. And all of these wearables need power. They all have batteries right now. They need to be recharged. So can we power them with solar energy? Well, some applications are better than others. So I'm not here to say that every single application is going to be solar powered. I don't think that's true. I think some key applications may be powered. So some of the innovations that are in on the sensor, sorry, it's not a sensor, on the photovoltaic side are ultra-thin organic solar cells that can be fabricated on fabric, and there's flexible ones. There's lots of research here, but not many are actually commercially available in terms of flexibles, but they are being developed, and in the future they will be commercialized. So those types of applications can enable wearable applications like a solar coat, solar backpacks, which I have seen, maybe a solar ski helmet, or maybe not skiing, or it could be outdoor activity. You want to do GPS tracking, you want to do head monitoring. These could be directly powered just by going out on your own, just from the sunlight. So back to this problem. So this is the product that I bought, and we tried to, charge everything. But the problem is that this was just put in a traditional way of put them all in series and then you're done. So what they did have a controller. I'm pretty sure the controller that was used was a very simple controller, probably a constant voltage control on the input, and all of the cells were put in series. And we already discussed how the series solution doesn't allow you to maximize all of them. And actually the one that is most shaded can create like a bottleneck. So that one panel, for example, one cell that's shaded, so going back to this one, even in this corner case, this part here has a larger negative effect than just maybe 5% is shaded, but it has an effect of 60%. And this one, 50% is shaded, but it has an effect of 95%, the reduction in power. So the problem is that we're just using traditional thinking and not actually applying it to a better solution. What I've been looking at and trying to advocate is actually a relatively simple one, going from series connected to parallel and bringing the converter to either a group parallel or an individual level in order to get better control of each of them while maintaining high efficiency for the whole system. Okay, so now I'm going to talk about how we're exploring panel converter architectures. So we wanted to make first a wearable bag with photovoltaic power to be able to charge mobile devices, for example, a phone, portable battery, activity tracker, something that's a relatively low power and runs about on 5 volts USB. But some of the problems with these applications is that if you have something that's in a bag or on a fabric, you're moving it around, you're going to have fast changes, you're going to have partial shading just from using it, and we're also going to have cells receiving different amounts of light. So we can't avoid mismatch here. So there's no way to get rid of the mismatch here. We have to just deal with it. So we have to do it through the converter design. We looked at using this parallel architecture. And at first we approached it from something we call differential power processing parallel. So parallel DPP, differential power processing. We use a series version for the series connected ones, but you can also bring the concept to parallel. And we wanted to look at this converter. This is a SEPIC converter. And if you put it here, it's kind of an odd architecture. The input is actually the total bus, the B bus, and the output is the difference between the PV panel and the bus. So if you added the voltage here, this would be the total bus, for example, 5 volts. And the output here would be a lower voltage. So I think if we're doing maybe 2 volts, and then this would be, for example, 3 volts, the PV panel. And by changing the output here, you're changing this PV voltage relative to the bus. So we looked at that and we developed a separate converter to do this. And the reason we want to do that is because by putting these two in series, you're actually reducing the voltage that you're processing. So you're not actually processing all the power through the panel. You're processing a lower amount in this case. So we looked at this and we're able to implement it. This is what would happen. This is just the diagram of current flow when you turn it on and off. So just as normal SEPIC, the single-ended primary inductor converter here, SEPIC, and we're able to process power through here, control this voltage, which controls the voltage of the PV. So we can control the PV at the maximum power point and reduce the total power that's being processed through it. And that's the approach that we wanted to take. So this is how it works. And we did develop these converters. This is our very early prototype. And so we wanted to show that it could work with completely different panels. So one is a very large panel, different voltage ratings, and a very small one with different voltage. So they both have different current and voltage ratings. And we're able to show that they do indeed operate with a standard maximum power point tracking algorithm called perturb and observe. We're able to control the power of the panel and give power to the bus. And we're able to show that you can disconnect and connect the load, and when you connect the load up here, it goes very quickly to the maximum power point and is able to track that. So we did a very simple solar powered bag prototype, not the most beautiful, but we're able to charge actually all of these basic devices. Here's a really simple video showing that work. So this is the panels on the bag. This is not charging because there's no light. Then we put some direct light on it from a lamp, and we're able to charge the battery. Then even when it's shaded, so one of the panels is completely shaded, it's still able to charge it. And we did also this with, I think, putting them in series, and it was not able to charge it. So it's actually a relatively simple solution here. And from here, we've developed actually quite a bit. So we've actually moved away from the parallel differential power processing, because some of them actually end up being the same as the basic topologies. So we ended up going forward with a standard boost topology, slightly different augmented boost topology that actually ends up having slightly higher efficiency. So that was our first prototype. Then we moved to some other prototypes later on. We're still working on those as well. So the next part I want to talk about is, in an application that's moving around, what kind of profile do we actually expect to see? Because we have these converters, we want to actually test them in realistic scenarios, but we need to measure that power to see what is realistic. So we put together this not very attractive bag. So we put these panels on a bag. At this time, we're still using rigid. Since then, we've moved to flexible, but we wanted to test it. There may be a condition where you have a moving object, but you have rigid panels on it. So we had 4 panels here connected, and we wanted to see, the ideal would be to get up to 4.8 watts is the rated power of this. But what happens when we actually put them in the sun? How much power we're going to get? So one of my students worked on a not very pretty board, but it is a current sensor device. And this measures the 4 PV panels currents, short circuit currents. And then we save that data onto an SD card. And then we calculated the G based on the proportion of the short circuit current. So we measured the actual panels themselves and figured out how they were changing to see their current, and then figured out the equivalent irradiance and then the maximum power point from there. And this is our data set. So when we took the data, the student was walking in the sun, and this is how the panels were arranged. And we measured the data at this time for about 30 seconds. And so what we got is, these are the results shown here. We have the short circuit current that was measured on the left. And you can see just from walking, it varies quite a bit. And even though the sun, I'll go back real quick, the sun here is, the sun itself is quite steady, but just basic movement that you would experience results in a lot of different changes here. So from the short circuit current, we can calculate the G here, is the irradiance, the amount of intensity of the light. So changes proportionally, you can see that. And then the power is going to be essentially proportional to these as well. So we can get the power from each of these, and you can see that PV1 is going to actually produce a little bit more. PV2, 3, and 4 are a little bit lower, but more similar in their trends. But you can see that they're changing relatively quickly, and it's not very steady. The total power that we get out of here is shown here, and it goes up to about 5 watts, or 4.8 was the nominal, but it also has some lower values as well. And we did some other tests, and they tended to be a little bit lower in power. So even if we have it rated at a certain value, we don't expect to get that in the varying conditions we're experiencing. Okay, we wanted to also create more of a hypothetical partially shaded. So maybe somebody walks by the panel very quickly, the 4 panels, and creates, reduces the power for each of these. So we created this other hypothetical situation with a very quick drop and quick coming back up. And these are the results from that. And then we wanted to compare the different system configurations. So one would be series connected. And then, so this is all in simulation, series connected panels with one converter, a buck converter. Then a parallel, a grouped parallel. So all of these are in parallel, and then they go to one boost converter to boost up to the 5 volts. And then the other one was the parallel. Here we're calling it DPP, but actually it's an augmented, it's a boost converter. So it's really an individual converter control for each of these. All right, so you can see that on the right here. When we put them into the 2 different cases, you can see this is the output power that we got. Oh, and we ran the same maximum power point tracking algorithm. So the control is essentially equivalent, the same control for each of them. And so we're trying to directly compare the different configurations here. And from here, we could see that the parallel mean, so the grouped parallel and then connected to one converter, and the parallel in DVP means individual converters here. Individual converters were essentially equivalent. Maybe the parallel one with individual converters was slightly better, but better than the series. And then this one where we have this kind of big drop in one of them at a time, it's a huge drop in the series. So you can see the power here goes way below when it's shaded and has a really low average power, whereas the parallel grouped together or parallel individual do much better. So this is just confirming our understanding that if you have these kind of mismatch conditions, you absolutely have to do parallel. You can group them together and they'll work pretty well in one converter, or if you do individual control, it can be beneficial in certain situations. Okay, so from that, we wanted to look at the actual controller of the converters to control the photovoltaic panel. And I'll try to wrap up quickly here. So we wanted to reduce the size. So eventually we want these converters to be very, very small. Right now they're still a little bit large, and we want them to be very, very small. And to operate each of the smaller panels, we need each of the controllers to be also low power consumption. So they need to be physically small and have low power consumption. but we still want to do active maximum power point tracking. A lot of the existing ones, they just do a constant voltage reference, and it's okay, but it's not going to work for, I think, all applications, especially when bending is involved in the panels. So we looked at an algorithm that would reduce, we could go very small, so we wanted a higher switching frequency, but we also wanted to reduce the losses. So burst mode is often when we go very low power, we go into a burst mode in converters, and we'll turn on our converter for a little bit and then we'll let it rest. And by reducing those switches, we reduce power loss. So we wanted to apply that to a maximum power point tracking algorithm. And so we looked at created a burst mode maximum power point algorithm that's based on very similar to a ripple correlation control, but different because it's using bursts. The idea is that you let the converter naturally go to some state, then you turn the converter on, burst, and then it will like affect it, and then it will kind of relax again, and then we turn it on whenever it gets to a certain point. So we use a hysteretic type of controller and then burst it on and off to control it. The idea is that when it's below the maximum power point, we see a certain curve in the voltage and the power. The voltage and the power are going to be directly proportional, whereas the opposite, if it's on the above the maximum power point, we're going to have inversely proportional voltage and current. So if we can measure the voltage and the power, sorry, not current, power, we could know which side of the maximum power point we're on. And if we get to the maximum power point itself, we would see that the power will have a kind of a peak and actually come back to approximately the same point after each kind of sliding back and forth here. So we used our augmented boost topology. So this is just the boost topology kind of rearranged here. It's the same thing. And we compared the traditional perturb and observe algorithm. I apologize, I didn't discuss that, but just that's the standard we're comparing it to the algorithm that we're proposing. And you can see down here at the gate signal, this one requires that the gate is constantly on and switching all the time, whereas this one is just switching on for a short amount of time and then stopping and turning on and off regularly. The ripple here is actually about the same in terms of the ripple that we see over the PV. So that we also want to reduce that ripple as much as possible. So we show that we can achieve that control. And then we use the real data from the experiment I showed earlier with we captured from the sunlight, use that as the shading case on the input, and then put it into the individual converters with our algorithm. And we were able to plot that, and we see that the maximum power point from the perturb and observe one, the standard that we're comparing it to, the burst mode was able to get just a little bit higher. This is not groundbreaking, but it is a little bit higher throughout. And the main reason for that is because the tracking efficiency can be a little bit higher. And so real power is from the simulation, the ideal maximum power. The red one is from the burst mode, and then the yellow one is from the perturb and observe implementation that we had. And if we look kind of more deeply at one point, we can see that the tracking efficiency, what happens with the burst mode is kind of more regular. You have this ripple at this amplitude, but with the perturb and observe, we observed that it was getting larger steps. So we're able to track more closely to the actual maximum power point and maximize the power just a little bit higher than the perturb and observe that we were implementing. Okay, so to conclude, we are still working on some things. So it's definitely not complete. We're still working on a lot of different ones. We have moved to some flexible panels that we're showing here. We're still developing and publishing that work, so I'm not sharing it here, but we're moving towards making flexible converters that can go work with flexible panels in a variety of applications. And the hope is that these could be, you could just get one with a converter on the back, and you can just implement it wherever you want. So on a wearable application, something else, vehicle application, drones, other things, anything that could be outside or inside. We're working on inside as well, but that's even further away. So to conclude, we want to enable future applications like vehicles, drones, wearables, and more. The solar characteristics we know change with irradiance, light intensity, and temperature. And in emerging applications, we cannot get rid of that mismatch. It's an inherent challenge, is that those characteristics are going to be uneven. So the first thing for these lower voltage applications, these emerging ones, we have to utilize, a parallel connection and individual converters when applicable, when it makes sense to put the converter at that level. In wearable applications, we're going to have light changing quickly, which we measured in some realistic tests. And we need individual maximum power point tracking control that maximize the power, but also have very low power consumption, both for the actual algorithm itself and also in driving and the sensors. So we want to lower the size and the lower power consumption, and then also look at smaller size converters, maybe higher switching frequency, smaller components. And so we've looked at a burst mode maximum power point tracking algorithm that we're still developing and finalizing. But the future, we hope to integrate all these different solutions into a very flexible converter that will enable photovoltaic power for a variety of different applications. I'd just like to say a special thanks to my lab and graduate students for their work in this. And I'm happy to answer any questions from any of you.
Okay, thank you very much, Katherine, for your presentation. It's been very, very interesting and informative with several examples where we can use solar energy and of course its challenges. Now it's time for some questions from the participants. So if you have any question, even in Spanish, si tienen alguna pregunta en español, la pueden escribir y nosotros la vamos a transmitir a la expositora. In our YouTube channel, we have received one question, and I will copy it to you in the chat so you can read it.
Yes.
Say Sumuk asks if would it be possible to use a Schmidt trigger to reduce the noise of the current derived above?
Okay, let's see. This is jumping very much into like a specific one. Let's see. So I'm not sure exactly. Reduce the noise of the current derived above. I'm not sure which part. Okay. So I'm not sure exactly which noise they're talking about. So I'm gonna skip that one because I'm actually not sure exactly how to answer that one. So I'll go to the second one.
Okay. There is the second one. Could you shed some light on semiconductor research that needs to happen or is happening to increase the efficiency of conversion of light to electrical energy in these cells?
Okay, so I am not an expert on this. I'm going to move back to the materials graph. So generally, the thing that I know about some of these emerging ones, for example, perovskite seems to be really big these days. The stability of these ones is really the problem. So I think material science people, not me for sure, people working on these have really are really doing a lot of work on this. And you can see from this plot, this is somebody, the NREL, they keep track of all of these. There's also a publication put out by Green every couple months that looks at the highest, all the innovations in solar cells. So if you're looking for those, look at, I think it's solar cell efficiency tables. One of the main authors is Green. That's a really good reference. And this plot is a good reference as well. I'm not the materials person, so I just know that they're working to improve the stability and get these numbers up here. just by the trend, it looks like there's still a lot of room to improve, because generally when you start to hit like the plateau, you see it kind of like stops, but it looks like these are still trending upward. So I think there's still a lot of room for innovation, but I am not the person to talk about that for these ones. It may be putting more junctions in, but that's usually more junctions are up here for these ones, and those are quite expensive and not cost effective.
Okay, another. One of the questions you mentioned about challenges in solar energy is how can we embrace solar PV cell mismatch while maximizing of the power and the solutions you mentioned were within the system and the power converter configuration, or use intelligent control of the converter at the converter level. And you have shown some practical example like the PV powered back. And could you comment a bit more about your experience and obtaining results? Is there still some challenges? What about the failure of one of the converters?
Okay, let me jump. Sorry. Okay, so the failure, I think, is what I can look at a little bit. Let's see. Well, this is one of the images. I'm trying to find one that's good to speak to. Maybe it's not going to be here. Okay, so when we have, maybe this is, I think the other one was better. Sorry, let me jump to this one. Okay, we'll just go with this one. When we have these individual ones, it depends on how something would fail. So if we have actually all of them in series, like all series and one converter, if any of the PVs have a problem where they disconnect, the whole thing goes down. And same in the converter. If anything in the converter fails, then depending on how it fails, if it shorts, then you lose all the power. If it fails through, it will just become a PV string. So you would have more points of fault with a single system. Whereas if you have a parallel system like this, it depends also how it fails. Generally, with silicon cells, they tend to, I want to make sure I'm not lying here, they tend to fail open because I think a lot of the problems that happen over time are wire disconnects, especially if you had something that's moving. It tends to be that the wires will become disconnected. And so they would be more likely to not short, but to be open. And so if in a parallel system, if something becomes open, for example, you lose a wire here, it just takes out that one, and the other ones are going to perform the exact same. Depending on the algorithm, the way we're looking at the algorithms, we're designing specifically to be able to be independent. So, and most of them I think would work independently because they're all relative to one point here. So they're all independently controlling each PV. Even if the converter goes down, if it fails in certain ways, it can still operate. The PV can just be a PV with no converter, and it will still provide power. It just won't be optimized. So I think that the parallel is going to be much better for faults if there's were to be a fault in the system. The only downfall would be if it something shorts the whole bus, then your whole thing's going to go down. But I think based on the architecture, it would be more likely to fail open or just take out one of the converters. For example, one converter would take out one of the PVs and the other ones would still be able to operate.
Super, thank you very much. Finally, based on your experience, how far are we to depend 100% of solar energy in our normal life?
Oh, how far are
What
we?
is your opinion? Yeah.
Okay, so how far are we from utilizing 100% solar power? I think we're very, very, very far, for better or for worse. I mean, solar power is one of the solutions. Just because I'm a researcher, I want to see, can we power as many things as possible? But truly, we're not going to power everything. We want to power solar power. If you look at the solar power generated by outdoors, even when it's not super bright, it's much higher than indoor. So indoor solar is just, it's at least 10, oh, maybe it's like 1% of the power from outdoor. So if you do indoor solar, the power is quite low. So you can only power very low power devices right now with the technology we have. So outdoors tends to be a lot more, make more sense. So any outdoor applications, I think we could utilize. It all comes down to the cost effectiveness and also increasing the market availability. So when the demand goes up, the development will increase and people will make the solutions. But a lot of things like solar cars, people are still not on board with, for better or for worse. But it's going to take a lot more development and cultural adapting. But I think solar will play a larger part in certain applications for outdoor use, maybe some indoor ones as well. And we're also going to see just a lot more coming into the grid, and battery storage and solar into our electric grid will also be very important. So I don't think we're going to ever get to 100%, but I think it has room to increase for certain applications, and maybe even get rid of the need for battery or battery recharging. That would be kind of another step of future, is we don't even think about charging or discharging, or charging or replacing batteries. We just go outside, things charge on their own from energy harvesting, and we can reduce our batteries completely. That's very far in the future.
Thank you very much, Katherine, for your answer on the presentation. Now I would like to give the microphone to Rodrigo Palma, the other organizer of these sessions. Rodrigo.
Thank you very much, Katherine. A very nice presentation and overview about these innovation options. I have one last question for you before to say goodbye to 2021. In our meetings, you are the last meeting in this year, so we are really happy with this excellent presentation. But if you can tell us a little bit about the entrepreneurship options in Taiwan, because your presentation is quite exciting in the sense that you open many new ideas, many options to apply photovoltaics in an innovative way. And I can imagine that this is a motivation source for students that will make startups, and they will create new business models and so on, of course, based on science. And if you can tell us a little bit how it will be promoted and work in the case of Taiwan, it will be great for us to hear about this.
Okay, so let's see, I'm still actually a little bit new to Taiwan. I've only been here for a couple of years, but I think there's globally around the world, there's lots of innovation specifically for students, because it's a great time to have the more far-reaching ideas, and people there are always investing types of events, especially at the schools here, and as well as when I was in the US. There's a lot of people who are willing to do startup competitions or put money into usually younger people, not always, but innovative ideas. And I think right now is a prime time for renewable energy, solar energy, climate solutions. It may not seem like wearable photovoltaics is a climate solution, but it is energy that reduces our dependence on our gasoline. So I think it has potential to get more funding. There's a lot more funding from green investors globally. And so for example, students who are interested, I think it's important to show the idea, make a prototype, get something working that you can show people, and move forward to be able to also shift, because things are shifting a lot in the investment space and in just the technology. So always be willing to shift and pivot your ideas. but you definitely have to start from like rooted technology that's working and then develop towards the solutions that people are interested in doing and funding. So I think it's kind of general for Taiwan and actually around the world.
Okay, okay. And do you have one example that you know from near about a successful case in this? If you can tell us about some bright idea, we just want to feeling.
See, I haven't seen as many. I'm trying to think of some of them. Most of them are not solar that I've seen, and a lot of them are actually in Silicon Valley. So right now in Silicon Valley, the green tech space is really improving, but people are looking mostly for carbon solutions, carbon offset, new carbon capture technologies, and different solar innovations and ways to improve the energy system, not just individual converters, but the whole energy stability system, I guess. So I don't have any specific examples, I apologize.
No, thank you very much. So again, thank you, Katherine, for your presentation, and thank you to all. I'll switch back to Spanish to say goodbye to this year. Muchas gracias por seguirnos. Siempre vemos caras que se repiten y nombres que se repiten en las presentaciones, pero también siempre gente nueva que aparece en nuestras presentaciones. Le agradezco a Marco con su equipo todo el esfuerzo de haber desplegado esto que parece súper simple, pero hay que hacer todo un proceso desde los contactos hasta llevar a cabo la presentación de una forma adecuada, junto con además dejar el repositorio para que quede como un valor de esto y que vaya más allá del momento en que se presenta en vivo. Así que les agradecemos mucho el que nos apoyaran, el que apostaran a seguirnos en este proceso y los esperamos el 2022. El 11 de enero ya les va a llegar la invitación, tenemos una primera presentación del año 2022 para continuar conociendo mucho más las opciones que nos entrega el sol. Y qué mejor que terminar con esta presentación que nos abre mucho la mente. So again, thank you, Katherine, for your presentation. It's the best end for this year with these bright ideas and innovation opportunities in the field. Thank you very much to all. Gracias, Marco, te doy el pase.
Thank you very much.
Okay. Thank you very much to everyone for participating this year, and especially to Katherine for support us at this time of the day and at this time of the year with this presentation. We say goodbye and we hope to see you soon in next year. Bye-bye.
Bye-bye.